Okay, so welcome everyone for this brag edition. It's a great pleasure to have this here at IMPA and to have you from Zoom remotely. So our first speaker today is Jardim from Unicamp, who will speak on higher rank DT-BP wall crossing in Bridgeland stability. Please, Marcos.
Thank you, Carolina, for the invitation and to setting this edition of the brag. Thanks everyone for showing up. So this is work that we've recently finished with these three co-authors. That's the third paper in a series. Every time we make a new paper, we add an author. So we started just me and Anthony Machocha, and then Christian entered in the second paper, and then now Jason Lowe in this third paper that we've been trying to study or to understand. Which one is? Yeah, to understand Bridgeland stability on threefolds. Right. So this is the main topic. So I'll try to be not too technical, right? And I'm not going to enter into detail what a Bridgeland stability condition is. Well, I'll say what a Bridgeland stability condition is, but in vague terms, and I won't dwell too much on technical details. Try to give try to give you guys the broad idea of this work and why we think it's nice and relevant. And my task today is try to explain this diagram, right? What this diagram means. So I'll come back to this diagram several times during the talk. So let me start saying what a stability function is, right? So on an abelian category, a stability function is some this button, yeah, some group homomorphism from the Grothendieck group of the abelian category to the complex numbers, satisfying these properties. So the imaginary part has to be non-negative, and the real part has to be negative when the imaginary part is 0. Right? So that's the rule. And these two properties of the negativity, the positivity or negativity, it only has to be satisfied for those objects, those elements, better said, those classes in the Grothendieck group that represent objects in the abelian category. Right? Otherwise, it doesn't make sense, because if it's a group homomorphism and it's a positive for some element, it's going to be negative for some other element. But those elements that are negative, they do not represent, they are not classes of objects in the abelian category. That's the point. Then you define what the slope is. This is the real divided by the imaginary part, as you expect. And when this imaginary part is 0, you just say that the slope is infinite, plus infinite. And then an object is semi-stable with respect to the slope if for every subobject in the abelian category, you have a smaller slope. So every subobject in the abelian category always has a smaller slope. And then there's this other technical condition of the Harden-Narasimhan filtration, that any object in the abelian category satisfies this filtration such that the factors of the filtration are semi-stable. So one way to understand semi-stability is that the semi-stable objects will be building blocks for all the other objects in the abelian category. Right? So any other object in the abelian category can be made out of semi-stable ones after successive extension. Right? So these are the building blocks that you extend several times, right? Extend and then extend again by semi-stable objects, and you get any object in the category. Right? So that's the one way to understand from the categorical point of view what is semi-stability. It's a way to choose building blocks out of which all the other objects in the abelian category will be made of. Okay? Bridgeland stability condition is a type of generalization of this notion of stability for abelian categories now to triangulated categories. Never mind too much what a triangulated category is. It's just some other crazy type of category that contains triangles in it, right? Because it's a triangulated category, so it's got to do something to do with triangles. But in the triangulated category, you have a bunch of abelian subcategories as sub-categories of the triangulated category. Right? And that's what I'm calling the heart of a T structure. Again, never mind too much what that is, but it's some choice of abelian subcategory inside the triangulated subcategory. Okay? That's what a heart is. So Bridgeland stability condition will contain these two bits of information. One is an abelian subcategory inside the triangulated category, and the other is a stability function on the for this abelian subcategory. Right? So the stability function, you don't have to test all the objects in the whole triangulated category, but only those that lie in the heart. Okay? And then again, an object is going to be semi-stable with respect to this pair. First, well, if it's a semi-stable object in the heart. So first, the object has to belong to the heart, and then you test whether every sub-object in the heart has a smaller slope. That's how you decide whether this is a semi-stable object. And there are two other technical assumptions that I'm just going to put here for completeness. Is that we always assume that that this stability function factors through a fixed finite dimensional lattice equipped with a norm. And all this has to satisfy something called the support property, another technical condition that is there to make theorems work, but I'm not going to dwell too much in it as well. So if there are any questions, stop me at any time. Okay. Good, so the mother of all examples is usual stability for bundles on curves. Okay. So in this example, the triangulated category is the derived category of coherent sheaves on a smooth projective curve X. Right? Then inside the derived category of any abelian category, but inside the derived category of coherent sheaves, you have one particular heart, which is just the coherent sheaves. Right? So this is called the heart of it has this fancy name, the heart of the standard T structure. Right? But any abelian category is always a subcategory of its derived category. Okay? So you have this standard heart, and there you can take this stability function, which is minus degree, and then the imaginary part is rank. So when rank is 0, this means that your sheaf is only supported on points, and degree will count how many points. Right? So whenever rank is 0, degree has to be positive. Right? So that's those are those positivity and negativity conditions for any coherent sheaf. We take this to be the lattice, right? Just cohomology lattice with this basis 1 and the 2 form, the Kähler 2 form, if you want. And tau will be this. Tau was that map that through which the z factors through, right? So the charge here, the stability function, will factor through this two-dimensional lattice, taking this map T, tau here. And in this context, Bridgeland stability is just the good old Mumford stability for bundles on curves. Right? So in this sense, this is the first type of stability that appeared, I guess, in the 70s. No, in the 60s, right? Mumford's work is from the 60s. 70s, and that it has been generalized in several different ways for higher dimensional projective varieties, and then to quiver stability is also a variation of that. Right? This notion of stability initiated by Mumford in the 60s has been generalized in several ways, and Bridgeland stability is the most recent installment of this successive generalization of this idea. Good. So some basic general results on this theory were established by Bridgeland when the first few papers he wrote on this topic. The first nice result is this Bridgeland deformation theorem that says that if you take the set of all stability conditions in a triangulated category, that has the structure of a complex manifold. Right? So first he says that if you take all these stability conditions, right, first you can define a topology on this set. It's a metric or a weak metric topology in this set. And with this topology, this forgetful map that just take the stability condition, which is a pair, right? A heart and a stability function. So you forget the heart, keep the stability function. Right? This map is a local homeomorphism. Right? Yeah.
So lambda was your lattice, right? So
yeah.
The stability function was from K0. So you forget the K0 part, but you just remember what happens on the lattice.
On the lattice, yes. Yeah. So the Grothendieck group of sheaves on a curve, right, is Z for the rank and Picard for the determinant. But you forget this information from the Picard group and just keep the degree, right, of the sheaf. Okay. And this is fixed and part of the theory, right? So in order to give this space a topology, you have to choose that norm and that lattice. So the lattice and the norm are fixed from the beginning, right? For you to define the topology here, and this map will be a local homeomorphism. So it's like a covering map, a covering map of this, this affine space. Okay. So this is just a big Cn, right? So C to the rank of the lattice or the dimension of the lattice. Okay. So in particular, it follows that stab is a complex manifold of complex dimension given by the rank of the lattice, which is the dimension of this hump here. Okay. So this is the first result, saying that all these stability conditions form a manifold, so you can continuously or holomorphically deform your stability conditions as you walk in this complex manifold. And second, that there is a wall and chamber structure. Right? So this means that in any compact set, there are only finitely many codimension 1 submanifolds called walls that divide this compact set into chambers. Right? So you look at the complement, this complement here of the compact set minus the codimension 1, real codimension 1 subvarieties, the walls, right? And this will give you a bunch of chambers. And these chambers have this following property. As long as you stay within a chamber and don't try to cross any walls, as long as you stay within a chamber, the stable objects don't change. Okay? So if an object is stable at this point, the analogy that I like to do is you are an ant, right, carrying a sack, carrying a bag full of objects in your abelian category. And you walk with a stability detector on your hand. Right? So as your ant is walking and he's looking at the stability detector, right? Though if you're walking within a chamber, the stability detector is green, and at some point you give one step, the stability detector becomes yellow. It means that you hit a wall. So some of the objects in your bag became semi-stable at that wall. And if the ant gives one more step, then your stability detector turns red, which means that one of the objects in your bag became unstable. Okay? So any object, it doesn't become unstable all of a sudden. Right? So it first becomes semi-stable at the walls, and then it becomes unstable. Okay? Not every object in your sack has to turn unstable all at the same time. Maybe just some of them become unstable. Right? And that's how how the set of stable objects, or the moduli space of stable objects, changes as you cross walls. Right? So that's the idea that you should keep in mind. Right? So as long as you stay within the chamber, the moduli space is the same. If you cross a chamber, the moduli space changes somehow. Good. So this vector v here, maybe I should clarify that as well. So this vector v in your lattice is playing the role of the discrete invariants that you fix in order to understand a moduli problem. So typically you want to classify all sheaves with given Chern classes. Right? So this is the role of this vector v. Yes, the map to the lattice is surjective. So any v is like the class of some object in the Grothendieck group.
But it's not covering, because otherwise it would be an isomorphism.
No, it can be an isomorphism, like in the...
Topology can be like trivial of the space of stability conditions.
What do you mean? Oh, if it just can be a product. No. I don't think it's just a product. In general.
On the source, maybe not local on the target. Is that because basically CN has no covering space.
It's simply connected, so if it were covering, it would be an isomorphism.
Okay.
It could be like an open set, for instance.
Yeah.
So that's local homeobase.
Yeah, it's a local homeomorphism. Yeah. Good. So some of the main problems that are studied in the literature about these things is first the existence of these things, right? For a given projective variety, look at the derived category of coherent sheaves on this variety. Does or do stability conditions exist at all in this variety? Right? So first question is existence. So we've seen the case of curves. For any smooth curve, you can find a stability condition. And then there's a positive answer for that for surfaces. For any projective surface, you can always find Bridgeland stability conditions. And for Fano threefolds with Picard rank 1, abelian threefolds, the quintic threefold, products of a curve with surface. Maybe this list is incomplete. I don't know. I'm sorry if this list is incomplete. And for higher dimensional varieties, the only examples that I know are Pn and the n-dimensional quadric. Okay? That the Peng that was doing a postdoc there in Campinas managed to find examples of Bridgeland stability conditions on Pn for any n and also for any quadrics. Okay. The other question is, well, what can you tell me about the moduli spaces, right? So this M sigma V is supposed to be the moduli space or the set of all sigma stable objects with fixed vector V, right? So that the objects in the Grothendieck category that lie over a given vector V in the lattice. Okay. Well, I think we're motivated by the Gieseker scheme, right? So by the answer that we know for moduli spaces of sheaves. So we would like this to be a projective scheme. Right? And the answer is yes. So this is a projective scheme, well, for curves, because it just coincides with the usual moduli space of bundles. But also for some surfaces like K3, P2, and P1 times P1. These are the ones that I've seen papers that they prove that this is a projective scheme. I don't think it's known in general for any surface. And the latest paper that I know is by this paper by Piriatny and Toda, but this is from 2015. So there hasn't been many very recent projects on progress on that, right? In where they prove that this M sigma V is a proper algebraic stack of finite type. Okay? So one of the main motivations of this new developments of moduli spaces without GIT, right, is motivated by this problem, to try to understand whether the Bridgeland moduli space is a projective scheme, because you cannot apply the usual GIT techniques to construct this moduli space as a GIT quotient. So you can set up a moduli functor, and the moduli functor will be a stack. That's the easy part, and then they prove that this is proper algebraic of finite type. Okay. So coming back to the picture, now in this picture, every point in this alpha beta plane corresponds to a Bridgeland stability condition on any threefold for which a certain construction holds, in particular for Fano threefolds and the quintic threefold, okay? With Picard rank 1. So each of these points, for each alpha and beta, you can find a Bridgeland stability condition on a suitable threefold. These curves in black and blue, the blue and the black curves, are walls, okay? Not the red one, but the blue and black ones are walls. And these are chambers, right? So there might be more chambers in this region, more chambers here below this, below here. But there are these two big chambers that go unbounded chambers that I'm calling here the Gieseker chamber and the PT chamber, right? That are so these are unbounded. There are no more walls to the left of this black curve and to the left of the blue curve. There are no more walls. And in this, one of the things we show in this paper is that in this region, the Bridgeland moduli space coincides with the Gieseker moduli space. In other words, for each of these Bridgeland stability conditions in this region here, the Bridgeland stable objects are just Bridgeland stable sheaves. Okay? Sorry, Bridgeland stable objects are just Gieseker stable sheaves. Okay? And on top of the blue line, it's the PT chamber, in which Bridgeland stable objects are PT stable objects. Right? I don't know what a PT stable object is, but I'll define it in a few slides. So I'll give you one definition of what a PT stable object is. And these two chambers are separated by only one wall, which is this blue curve. Okay? So this is where the DT-PT correspondence will occur. Right? So PT is obvious, and then this a different name, a fancy name for this Gieseker chamber is the DT side of the story. DT stands for Donaldson and Thomas, after a paper that these two authors wrote, I think in the beginning of the 2000s or late 1997.
Okay? Marcos, can I make a naive
yeah, sure.
question? So what about slope stability? Are they stability conditions in your sense?
Sometimes Gieseker stability coincides with slope stability. For some values of that V, Gieseker coincides with slope. Right? So slope stable is always Gieseker stable, but not the other way around. So you may have objects here that are not mu stable, right? But every mu stable sheaf will be in this chamber. Okay? Yeah.
Can I ask another question? So when you change chamber, the stable objects change, right?
Yes.
And the stable objects that's in the Gieseker chambers are nested out sheaves, right?
Yeah.
Belong to the kind of standard part for the arbitrary construction.
Yes.
When you change, presumably is it always the case that some of the objects no longer, does the heart of the correspondence structure always change, or do you have some cases where adjacent chambers have the same heart?
No. The heart changes, right? So these PT stable objects are going to lie in different hearts. But what can happen is that these walls are like fake walls, in the sense that the stable objects don't change. I'll show you one example in which that occurs.
But
right?
It's always the case that the heart changes?
But it's always the case that the heart changes. Right? But it's just an object that belongs to both hearts. Okay. Good. So, So these notions of PT and DT stable objects and their moduli spaces were introduced. The DT is for Donaldson and Thomas, the PT is for Pandaripande and Thomas, and they are introduced for some enumerative geometry reason, right? So I'm really no less than zero about enumerative geometry. So my knowledge of enumerative geometry is numbered 0. The count is 0. But the DT-PT correspondence in the title is supposed to give you a way to transform the DT count to the PT count, whatever that means. Right? So it's some rule that tells you, so if you know how to count objects on one side of the wall, then you know how to count objects on the other side of the wall. Right? So this is the DT-PT correspondence. For me, what I'm calling the DT-PT correspondence is that these two moduli spaces are related by a single wall. There's a single wall crossing that changes the Gieseker semi-stable sheaves to these PT stable objects. So this is the main words on the title. Okay. So let me try to...
Is this for a specific V? This picture is for a specific V?
No, for any, not for any V, but as far as we can prove is V's for which so the V has 4 entries, right? So for a threefold, the V will have 4 entries. If the first 3 of them are co-prime, right? So if they only have the GCD of them is 1, then this picture holds. No, yeah. So the heart changes from one point to the other. So in both chambers, the heart is changing from each point. The heart changes. Right? So, but it turns out that the coherent sheaves, the stable objects, which are the stable coherent sheaves, are always in the heart. Right? So the heart is changing here as you give one little step, but the Gieseker semi-stable sheaves always stay there. And on the other side of the wall, the same thing. The heart is changing, but the PT stable objects, right? And the heart on one side of the blue wall, above the blue wall, and below the blue wall, these are very different. So the heart that contains the PT objects is different from the standard heart that contains the Gieseker semi-stable sheaves. Okay. Good. Now, to explain what is dt and pt stability, let me talk a little bit about Bayer's polynomial stability. So it's a notion, it's a variation of the stability condition on an abelian category or on a triangulated category. But instead of the stability function taking values on complex numbers, it takes values on polynomials, on polynomials with complex coefficients. Right? So it's, again, some... And then you have to explain, say something about those positivity and negativity assumptions. And this is what's replacing the positivity, negativity, which is that when m is very large, so asymptotically, when m is very large, the value of this polynomial will tend to a given phase, right? So they will always, as m becomes very large, this phi will be restricted to an interval from a to a plus 1. Right? So as m becomes very large, the phase is moving, but it's moving within a half plane. Right? So phi cannot. So this phase belonging to an interval like this means that the phi always belongs to a half plane on the complex numbers. So it's not like when m becomes very large, it's not like the vector is rotating crazily around, but it's restricted to some half plane. So this is the... Yeah.
What do you mean by heart? Is it like a sheaf on, is it like special sheaf on X?
No, a heart is an abelian subcategory inside the triangulated category. The stability means this, that every subobject has a smaller phase when m is very large. So it's kind of asymptotic as well. And Z is supposed to have the Hadamard-Zeeman property as well, right? So you always have a filtration for which the factors are semi-stable. So this is Bayer's stability, polynomial stability. Yeah, maybe I'll skip most of, never mind too much. It's too technical what is above here. But the key thing is this, right? So you can write a polynomial function like that, a polynomial stability function like that, in these terms, looking at the various Chern characters and powers of m. Right? So here is supposed to be a CH cube instead of CH0. So this rho 0 CH cube, rho 1 CH2, right? So that omega CH2, that's a number, omega square CH1, that's a number again. So these are all numbers. And rho are complex numbers. Rho are vectors in the complex plane, in R2. Right? So you can write your polynomial like that. And then the dt and pt differ by the particular ordering of these rows as complex numbers. Right? So if you put the rows in this position, 1, 0, minus 3, and minus 2, so essentially if you invert, so the difference is here between 0 and minus 3. They are in inverted position from one side and the other side. Right? So if you take the rows in this position, this is what we call the PT, polynomial stability. And if you take the rows in this other position, that's what it's called the PT. Okay? And the reason behind that is that what Bayer proved is that if you look at this configuration of the rows of those phases, the polynomially stable objects are Gieseker semi-stable sheaves. And what he proved is that for this configuration, and the objects have rank 1, So the first entry of that lattice is 1. So if the objects have rank 1, then the polynomially stable objects will coincide with what Pandaripandi and Thomas introduced as PT stable objects. Right? So Pandaripandi and Thomas, in their original paper from 2000 or 1998 or something, they introduced this notion of stability only for rank 1 objects. Right? And this is then what Bayer does. He compares the rank 1 objects, the rank 1 stable objects, with the polynomial stable objects for this configuration of the roles, and then he shows that there is one wall in the space of polynomial stability conditions that separates the dt from the pt. Right? So this is Bayer's result from, again, from 2000 and maybe 2010, a bit less than 2010. And since then, since Pandaripandi and Thomas' work and Bayer's work, people have been, pondering, asking if similar thing would also be true in Bridgeland stability, right? So if there is only one wall separating the dt from the pt. And this is important for these enumerative reasons that I don't understand. So here's a reminder of what is a Gieseker semi-stable sheaf. So Gieseker semi-stable sheaf, you compare this other so-called Hilbert polynomial, right? This is the reduced Hilbert polynomial, right? The Hilbert polynomial divided by the rank. And again, you do this comparison asymptotically, right? So you say that a sheaf is, a coherent sheaf is Gieseker semi-stable if this reduced Hilbert polynomial is less than the reduced Hilbert polynomial of the ambient sheaf when m is very large. And then there's, yeah.
So just the first time you put this picture of the wall, you don't have to go back. When you wrote this picture the first time, you were saying Bridgeland stability.
Yeah.
There were polynomial stability?
No. Bridgeland stability condition is not a polynomial stability condition.
Right, but how do you, but the Gieseker stability is a polynomial stability.
Yeah. Yeah.
And then the results you just stated were about polynomial stability.
Yes.
So how do these relate to the
Yeah.
original picture, whether it's Bridgeland stability?
Yeah, so the fact is that the polynomial stability is like an asymptotic version of Bridgeland stability. So if you take back in that picture, so if you take, let me put it this way, if you come to this corner of the plane when beta is very negative and alpha is sufficiently large, then the Bridgeland stability sort of converges to a polynomial stability at infinity. Right? So the
So you can show there's a single chamber there's a single wall in the Bridgeland world by showing it.
at infinity, yeah, yeah. So one way to think about it is, this is actually something that, we've discussed among ourselves, sort of know this has to be true, but nobody sat down to prove the details, right? But I think this gives you a good, at least informal picture, right? So you can think of straight lines emanating from the origin and going off to infinity, right? So a bunch of straight lines. And you look at stability, we have a notion of asymptotic stability along the line. For each line, you can tell what is an asymptotically stable object. An asymptotically stable object means that an object that stays in the heart, from one point onwards, it stays in the heart, and it becomes stable after a point onwards. Right? So this asymptotic notion of stability, as you follow the different rays emanating from the origin, right? Which means that if the slope of the ray is less than 1, then you get dt polynomial stability at infinity. If the slope of the rays is, I should say, smaller than -1, right? So if the rays are like this, right? So below this hyperbola, the slope of the hyperbola is -1. The slope of the asymptote of the hyperbola is -1. So if you are inside the mouth of this hyperbola, right? So you get to dt stability, dt polynomial stability. And if you are above the hyperbola, you get to pt polynomial stability, right?
This is always the case? This is not just the dt-pt situation?
No, yeah. So what happens is that the dt-pt situation of Bayer, right, is an asymptotic version of Bridgeland stability.
So do you have statements like there exists a Bridgeland stability if and only if there exists a polynomial stability?
No. This is specific for threefolds, right? For surfaces, I don't know if this claim is true.
But that's true for threefolds?
This is true for these threefolds, like Picard rank 1, Funnel Picard rank 1, the quantic, the quintic, or the abelian threefold. For these threefolds, what I claim, well, it's very close to true. Let's put it like a simplification of truth. Okay. But for surfaces, there's a different story, and I don't know how it goes. But it's a good question also. Okay. So I was recalling here what is Gieseker stability, and there is a variant of Gieseker stability, which is 2 Gieseker stability, in which you compare, you make similar comparison, the same inequality, but without the independent term, without the t to the 0 term, right? So you cut off part of the Hilbert polynomial, and you compare what remains, right? So this is the notion of 2 Gieseker stability, and it's something that sits between mu stability. I didn't put here, but it's something that sits between mu stability and Gieseker stability, right? So the chain of implications is that mu stable implies 2 Gieseker stable, implies Gieseker stable, and then Gieseker semi-stable, 2 Gieseker semi-stable, and mu semi-stable, right? So it's some variant that interpolates between mu stability and Gieseker stability. And as I mentioned, one thing that Bayer proved is that this is dt stable objects in the polynomial sense coincide with Gieseker semi-stable sheaves. Good. Now let me give one definition of PT stable objects, the definition that is easier to give in my context here. And it goes like this. They can be described in terms of a triple, at least in this condition, which is the same condition that Carolina asked me, the same condition that I gave you in the... So if churn 0, 1, and 2 are co-prime, PT stable objects can be described as follows. You take 2 Gieseker semi-stable sheaf with this satisfying this other technical condition that the homological dimension has to be this sign is inverted, is less or equal than 1. Sorry about that, right? So it's 2 Gieseker semi-stable sheaves with homological dimension at most 1. Never mind too much what that is. And 0-dimensional sheaf and a morphism in the derived category from P to B shifted by 2, or some X2 class, some X2 from P to B. Then every PT stable object is given as the cone of this morphism here, right? So the cone of from P to B2, right? So if you take the cone in the derived category, that's going to give you a complex. This complex has 2 non-trivial cohomologies. One cohomology is B, and the other cohomology is P. Right? So you can think of this as a 2-term complex that has two non-trivial cohomologies. These two sheaves B and P. So this generalizes the notion of rank 1 PT stable pairs that was introduced by Pandaripand and Thomas in their paper. Well, they are, and by a PT, the definition of a PT stable object in this talk, because I'm comparing two things that I'm barely defining, right? So it's probably very confusing. So okay, so in this talk, PT stable object is an object that is stable in the sense of Bayer's polynomial stability when the configuration of the rows is given. Is given like this, right? So take this configuration of rows, look at what are the polynomial stable objects, and these are what we are calling PT stable objects. Okay? And then these PT stable objects can be described in more sheaf theoretical terms, in terms of these things that I'm calling stable triples. Okay? Completely non-trivial means that, so yeah, I'm going to have to write this. So this cone A of eta will will fit in a triangle like this. Meaning that B is the H-1 cohomology and P is the 0 cohomology. And complete non-triviality means that no subsheaf of P factors through A. This is the complete non-triviality. Good. Now this is the DT-PT wall crossing. That's what happens when you cross the blue line from the diagram. So on this side, this curly G is the Gieseker moduli space for some fixed Chern numbers. And on this other side here is the PT moduli space, the curly T. Now, these morphisms are given as follows. So, starting with a Gieseker semistable sheaf E, you produce these sheaves E prime and ZE. Right? ZE is the maximal zero-dimensional subsheaf of this quotient. Right? And E prime is the kernel of this thing here. So, the kernel of this thing is, you can show that if E is Gieseker semistable, the kernel of this thing will be a 2 Gieseker semistable sheaf, and it will have homological dimension at most 1. Right? Because I'm precisely, this ZE here is precisely killing the bit that would give, that could give an X2, right? A non-trivial X2. Right? So this is the zero-dimensional sheaf and the 2 Gieseker torsion-free sheaf, a 2 Gieseker semistable torsion-free sheaf. And this square bracket here is supposed to mean S-equivalence class. S-equivalence class in this Bridgeland moduli space. So beta bar, alpha bar are points on the blue line. Right? This is the Bridgeland moduli space on the blue line. Okay? And then I'm taking S-equivalence classes of these objects. Well, I'm claiming here that these will be Bridgeland semistable at these points, beta bar, alpha bar, and I'm taking S-equivalence class of this thing. And on the PT side, you just take the cohomologies, the H-1 cohomology and the H0 cohomology, which are precisely the, oh, it's a virtual thing, so I cannot point to the to the blackboard. So the h minus 1 is the b that I wrote here on the board, and the h0 is the p. Good, so that's what these wall crossing maps do.
Sorry, can I ask a question?
Sure.
This G minus V, T, V, those are DT and PT modulators, right?
Yes.
And DT and PT are polynomials.
Well, yeah, in principle they are polynomial stability.
And then the thing in the middle is
Bridgeland stability, right? But the G and the T are also Bridgeland, right? So in these in the chambers, right?
right.
The G is a Bridgeland moduli space here, and the T's are Bridgeland moduli space here, right?
And these are birational.
No. Okay. Not in general. They may be in some cases, but not in general. So very recent, few months ago, these two guys proved that the PT moduli space is projective. So this gives you an answer that on those unbounded chambers, the Gieseker, the Bridgeland moduli space are projective, because on one side, below the blue curve, they coincide with the Gieseker moduli space, which we know is projective, and above the blue curve, they coincide with the PT moduli space that these guys just proved it is projective. Okay? But we don't know whether the moduli along the blue line, whether or not it's projective. This is not clear yet. Good. This gamma is an analog of the Gieseker to Uhlenbeck map for threefolds. If you don't know, forget this line. If you know, you may find this observation interesting. In general, this map, gamma here is dominant, right? So any sheaf here, any object here, can be traced back to a Gieseker semi-stable sheaf, but this map here is not dominant. Right? So you may have things here that don't have a pre-image on T. And the wall crossing is not a birational transformation. Most definitely, in this case, unfortunately. Maybe I'll get to the case studies in this iteration of the talk. Okay. The case studies. This is an example of here. X is a smooth threefold. The first example, well, these two examples, works for any smooth threefold with Picard rank 1. Right? So there is a situation when you take the V to be this R00 minus n, then the Gieseker moduli space is just a quotient, just a quad scheme, a quad scheme of OX R copies, while the PT moduli space is just empty when n is non-zero. Right? So this is a situation where the wall crossing is a killing wall. It destabilizes everybody. And this is the other opposite example in which this is a fake wall, right? In which the objects cross the wall without suffering any change. So all the Gieseker semi-stable sheaves for these vectors, I didn't explain what's V3 max, but there is a vector, there is a choice of vector for which the walls don't suffer anything when they cross the wall. Right? So that's what I'm calling this a fake wall. And then this is a very precise example of an honest wall. So if you take these sheaves, this vector space, then I know precisely what is the Gieseker moduli space. The Gieseker moduli space is going to be birational. On an open set is a P1 fibration over P3 times P3. Right? So that gamma map is just goes to P3 times P3. away from the diagonal in P3 times P3, the fibers of gamma is P1, and over the diagonal, the fibers are P2s. Right? But this thing is irreducible. So this thing is irreducible that has this, strange structure. And while the tau map only maps to the diagonal. Right? So the image of the tau map is only above the diagonal. Right? And this is an isomorphism. Right? So it changes dimension, changes everything. So on one side you have a 7-dimensional moduli space, on the other side you have a 3-dimensional moduli space. Good. So a vague idea of the proof. Did I put the picture again? Yeah. So, 2 minutes for a vague idea of the proof. So in previous papers, we looked at the asymptotic stability that I was explaining to Olivier. Right? So if you go to infinity horizontally, meaning if you go to infinity in this direction, the asymptotically stable objects are the Gieseker semi-stable sheaves. And if you go to infinity vertically, the asymptotic Bridgeland stable objects will be some class of perverse sheaves that particular characterization will depend on beta. Will depend on which vertical you chose to go to infinity. But when beta is sufficiently negative, this stabilizes. Right? At some point after beta is sufficiently negative, it doesn't change anymore. Right? The asymptotic behavior doesn't change anymore. Oops. So as B becomes sufficiently negative, the vertical asymptotics will coincide with the stable triples, which coincide with the PT stable objects. Okay. So we first show that asymptotically, we characterize what are the asymptotically stable objects when beta is very negative or alpha is very positive. Then we characterize what are the stable objects at the wall, and then a little bit below the wall, a little bit above the wall, and then we show that there are no other walls. Right? So after the black curve, there are no other walls. Right? So since we understand what is stable at infinity and near the blue curve, and there are no walls, then it can change. So the whole thing has to be a single chamber. That's the gist of the argument. Here are some references, the 3 papers that I mentioned to you, and there's a link for a YouTube talk here in which Christian gives a talk about the same topic. And thank you.
Questions for Marcus?
So here's the list of the threefold. So Fano threefolds, Picard rank 1, abelian threefolds, the quint threefold. But since we are assuming Picard rank 1, you have to exclude product of curve and surface. Right? So just these are concrete examples of threefolds for which this whole theory works. But more generally, is any threefold for which the Bayer-Macri-Toda construction works. Okay? And these are examples of.
But in principle, could it work for a threefold category? I mean, with using under some assumptions of the K0 group or something like that?
Yeah, I think so.
You don't really use the geometry of the underlying threefold.
In a sense, yes, because what are Gieseker semi-stable objects on a threefold category? I don't know. What is the analog of? So I guess we are using the geometry somehow because we need these concepts of Gieseker semi-stable sheaves and stable triples. Okay.
More questions?
When you wrote for some beta, the vertical.
You said that for some beta, the vertical asymptotic was perverse sheaves. Can you elaborate? Do you know which betas that's the case? Or?
Yeah, we managed to find at least some estimate, probably not a sharp estimate, of what it means to be sufficiently negative, right? So here the idea is that but when beta becomes sufficiently negative, then the asymptotics doesn't depend on beta anymore.
But I was asking about the vertical in the perverse sheaves case.
Okay, yeah. Well, it's you can characterize, right? So they are if they are semi-stable along some small beta, then it looks a bit like this, right? So it's going to be They are going to be objects with only two non-trivial complexes, with only two non-trivial cohomologies. One is a semi-stable, in principle, a Gieseker semi-stable torsion-free sheaf, and the other will be a one-dimensional sheaf, right? And that satisfies some versions of this complete non-triviality that Daniele asked me. Right? So it's the basic structure is this, like a two-step complex, but the particular sheaves will satisfy slightly different conditions.
So what you're saying is the stable ones are they are all perverse sheaves.
Yeah.
But which ones you get depends on beta.
Yes,
okay.
yes.
Thank you.
So they will satisfy some inequalities that depend on beta.
Great, thank you.
Any more questions for Marcos?
I have a maybe simple naive question, but maybe I missed what happened on the case of the red color.
Oh yeah, the red. The red is not important for this talk, right? Yeah. Nothing happens in the red curve, right? So it's just to make it more colorful. No, it has an interpretation. It's the last tilt wall, right? But maybe what's most relevant for this talk is this black dot here, right? So this there is a weak notion of Bridgeland stability, right? Or for threefolds, a weak Bridgeland stability, and this red curve is a wall for this weak notion of stability, right? And it's so-called last tilt wall, and the highest point of this the intersection of this last tilt wall with the blue curve gives this point where. So what is the role of this point here? It means that above this point, along the blue curve, a little bit above the blue curve, you get the PT, stable objects, and a little below the blue curve, you get the DT, stable objects. You get the Gieseker semi-stable sheaves. And that happens from this point onwards, right? And this point is characterized like that. It's the last tilt wall along the blue curve.
More questions? Do we have any question in the Zoom? No? Okay, so let's thank Marcos again.
Thank you. Thanks, Carolina.